channel C&D, Mr. Vitor. Vitor. There you go.
Thank you. Okay, so I was kind of a little bit lucky to choose this topic for today because Go concurrency has already been mentioned in a few talks today. We've seen people talking about how to do macros in Clojure to emulate the same thing. We've seen people talking about async patterns in JavaScript that try to emulate channels. So there is a lot of good stuff about the Go concurrency model, and this has been talked about in several different communities, and several different programming languages are trying to use the same ideas. So if you heard about anything about the Go language, you certainly heard a little bit about the concurrency model. How Go concurrency is one of the strong suits of the language, and how it's powerful, and how you can build really great programs using several building blocks of the language, such as channels and goroutines. But what are those things? How do we use them on real programs? How do we use on a daily basis to build software that we can deploy into production, and how we can do batch processing and apply it in HTTP apps, and everything that we want to do with concurrent software. Channels are simply blocking queues. If you came from any other language that has this concept, such as the blocking queue class in Java, that's pretty much the same thing. The difference, the strong point of this is that channels are part of the language. They are a first-class citizen. The runtime of the Go language understands that channels exist, understands that they block, and this is a simple concept that's very powerful, and we will show how it allows us to synchronize several different parts of our programs. The fact that channels are blocking means that when we try to read something from a channel that does not have something to send, or when we try to send something into a channel that is not ready to receive data, the piece of code that we are running doing that operation is going to block. And this might seem strange at first, but this allows us to do a lot of things at the same time in our program and change between them easily and seamlessly and naturally, with the runtime controlling things for us. The basic syntax is extremely simple. To create a channel, you use the make keyword and the chan keyword, and you can create a channel of anything. I used an int in this example, but I could have used a string, I could have used a slice, I could have used a complex struct, I could have used any parts of the language. Everything is available. Sending something into a channel is basically just that arrow operator. You send something into it, and receiving is the same operator, but in the other side. So you just get something, you pick something out of the channel. You can think of the arrow that way. And when you close the channel, just call the function close. This means that that channel cannot receive any more data. It can still deliver data if there is data inside that channel, but it cannot receive anything else. And if you want to read everything that is on a channel until it is exhausted, until it is closed and there is no more data in it, you can use a for loop with the range keyword. So you just do range and name of the channel, and then you will receive data whenever there is data inside that channel. So think about as if it was an infinite loop, and you do the receive operation that we have a few lines above, and you do that until there is nothing else in the channel, and you have read everything, the channel is closed, so you know there is no more data coming, and the for will end by itself when that condition arrives. A Go routine, which is the partner of the channel to build concurrent programs, is the equivalent of a lightweight thread. So an operating system thread is heavier compared to a Go routine. So an operating system thread is allocated with a lot of memory, and a Go routine is not. So a Go routine is allocated with only a little bit of memory, and it can grow as the program develops. If you use more memory, the runtime of the Go language will adapt as necessary and will give you more memory. And because of that, we can have many Go routines at the same time, because they are really light and they can grow as necessary. We can have hundreds of Go routines, we can have thousands of Go routines. They are scheduled into the operating system threads, and they are light enough that you can run a lot of them. The runtime of the language knows about the blocking operations in channels, so this is what makes it efficient. If we are running a Go routine that enters a state where it would be blocked by a channel operation, the runtime knows that it can context switch at that moment, and when it context switches, the program will continue running with another Go routine. So there isn't a huge cost to be paid by context switching with an entire operating system thread, and this can happen very frequently and a lot of the time, so there is always something running, and that's why you can spawn lots of goroutines and not worry about it. And the basic syntax is even simpler than the basic syntax of the channels. There is just the go keyword. You just use the go keyword in front of any function. Any function call of your program can become a goroutine, and that's all you have to do. You just put the go keyword in front of it, and this will spawn a goroutine and will run at the same time as the goroutine where you did the call at the first time. When we put both of those together, which is what we want to do, of course, it's very simple. Channels can be passed as parameters normally. There is nothing special about it. So you just declare any function and you call it with the go keyword, and you pass a channel as an input, as an output, and the channel can be shared by code outside and inside the goroutine that you're calling. So a part of your program can send data into it, and the goroutine can read data from it, or the other way around. And another thing that you can do is that in the second example here, we can define the direction of the channel. This means that when we create a channel, we can send data into it and we can receive from it. It has both ends. But inside the specific function, you can define that in that function, you will only have read operations, or you will only have write operations. So you can treat a channel as only an input to the function or only an output to the function. And this is checked at compilation time, because Go is a compile language. So if you try to do an operation inside one of those functions in the other order, so you receive a channel which is only an input to you, and for some reason you try to send data into it, your program will not compile. You will not be able to make that mistake. So it's the same operator, those arrows that you use to send and receive data, and the difference is only the position to define if you're trying to read from the channel or send to it. It's in one case it's on the left of the chan keyword, on the other case on the right of the chan keyword. This is kind of arbitrary, so if you want to remember this, it's right to left, because someone thought this was a good idea, and it's right to left. So if you have it right to left, the input channel in my example, you can only read from it, and on the output channel, you can only send data inside the channel. But you gotta do synchronization too, because if you're gonna split your program into several building blocks and you're gonna run them concurrently, perhaps you're gonna run them in parallel as well. How do you know when one of the things that you spawn in your program, one of the goroutines that you send running, has finished? So if we don't do anything about that, our program is going to run, and it's going to spawn a lot of goroutines, and the first goroutine, the main goroutine of the program, is going to end, and then the rest of the program will terminate immediately, and we won't have time to do all the work that we were trying to do in the other goroutines. So one of the easiest ways to wait for a goroutine to end is to create a channel just to do that. We are not interested, in this case, in the thing that we are sending into the channel. It's the operation of sending something into it. It signals that we are telling the other part of our program that we are done. The goroutine is telling the rest of the program, I finished doing my work. So in this example, we are starting two goroutines. The functions are anonymous, so we are declaring and calling them immediately. And the last thing that each of these functions does is send a sentinel value into the channel. It's just a true Boolean in this case. It could be anything else. Often another example for this is an empty struct, which doesn't use any memory. So, and outside the goroutines, we just wait for the channels to receive some data. So in this case, we know that we have two goroutines, so we read from the channel twice, and then the program is going to block at that point and wait for the goroutines to end and do their work completely. This isn't very refined, because we can think if I'm going to have several goroutines, I'm going to have to read from this channel as many times as I have goroutines. So it is a way to do a simple program, but not a very good way. So the standard library of the language gives us better options. So a better way to do synchronization is Waitgroups. So there's a package in the standard library of the Go language called sync. So it's always available. If you have the language, you have access to this package as well. So one of the things that the sync package gives us is a Waitgroup struct. So this Waitgroup basically hides from us a counter that is safe to be used in several goroutines at the same time. And we can use this counter to block our program and wait for several goroutines to end. So in this example, instead of sending data into a channel, before I start a goroutine, I just add one to the counter of the Waitgroup. And then I start my goroutine, and the first thing I do is I defer an operation called done. This done operation basically decrements my internal counter by 1, And the defer keyword is not directly related to goroutines and channels, but if you have never seen that before, it means just run this operation when my function ends, whenever I return. And it doesn't matter if I have several returns inside my function. The last thing that is going to happen after my return is the call I set on the defer. So this is very useful for closing resources, and in this case, it's always is useful as well for guaranteeing that I'm always gonna decrement one from the channel, from the wait group, whenever my goroutine ends. So my two goroutines now, they add one to the channel before I start the goroutine, then I start the goroutine, and immediately I set up an operation to say when I end, I'm gonna decrement. And then outside the program, I just do wg.wait, waitgroup.wait, and the wait group is gonna block on that point, and the wait function is not gonna return until I reach 0 again. Which means whenever all the goroutines are finished, whenever all the goroutines have done all their work, then the wait's gonna be 0 and it's gonna unblock. So we can think about this as a semaphore. We are not using that name, but a wait group's basically that. When we add something, we are blocking a goroutine, and when we are waiting, we need to wait for our semaphore to turn green, which is when it reaches 0 on the counter. When we use all of that together, we can split the program into several workers. So if you can think of your program as a series of separate tasks that can run concurrently, they need to pass data from one to the other, but they are independent. You could run them in parallel easily or concurrently with channels and goroutines. Each task may or may not run in parallel, and you may have several degrees of parallelism. So if a piece of your program is slower than the other pieces of your program, you might want to run it with more parallelism than the rest of the program. And what I mean is this. So this is almost a real program. So one of the workers could work like this. So we use Waitgroup to control the synchronization. So that is a Waitgroup that comes from outside that worker. It's created on the main of the program, or it is created by whatever call this worker. And it has an input channel, an output channel, and a degree of parallelism. All of this is configurable, so you might receive that degree of parallelism by a configuration struct. You might read it from a file, you might read it from an environment variable, a flag, or anything else. From the point of view of your worker, you're just receiving some data from outside to tell it how much parallelism it should have. Well, the first thing we do, again, like the previous example, is just defer the dawn operation. So I'm telling the semaphore from the outside of the program that I'm gonna decrement something when I end this function, this worker, and then I create another wait group. I could do only one wait group for the whole program, and then it would control all the goroutines at once. But I like to do this pattern with one wait group for each worker, because this allows us to think of each of these workers of the program as an independent block, as an independent entity. So if you are developing something in one specific part of your program, if you're developing one of your workers, you can look at your function that is doing that work, and you don't need to think about the rest of the program, because they all have the same face, the same pattern, so they will all behave the same. So after you start the wait group and you add to it the degree of parallelism, you start as many goroutines as you described before, which is the level of parallelism that you want. So we do a simple for, and inside the for we just call a function with a goroutine, and inside of that function we use the internal wait group of this worker, and then we range into the input channel and read everything from it and do whatever work we need to do. And when the work is done, we just send the output of our operation into the output channel and say, okay, this is not my problem anymore. Another part of the program is going to handle the next thing that we need to do. So all of these routines will run at the same time. They will be started together, and they will all consume data from the input channel. And there will be no contention and no race conditions or anything, because reading from a channel is an operation that is part of the language. It is controlled by the runtime. So whenever there is new data in the input channel, it is going to be distributed naturally between all of the goroutines that are running at the same time and reading from the same channel. So after we start all of those goroutines, we again wait on the wait group. We wait for all those goroutines to completely consume the input channel, and after that we close the output channel, because in this example each worker is responsible for one channel. So whenever this worker ends, you can say, I am the only one that is sending data into the output channel, so I can close it to signal to the next goroutine that I'm not going to send anything else. So the goroutines in the next part of the program can end their own for loops, can end their own consumptions of the channel, and they can finish processing. And that is a visualization of what this means. This animation is not exactly the same example that I showed you before, but it is pretty similar. So you can think about the main goroutine starting a big goroutine that is coordinating all of the other, and then the cylinder, this things. Each one of those blue vertical lines is one of the goroutines, and we can think about the red arrows as data passing from one to the other. So if we think about all of these workers, your program running several workers at the same time, they are just going to be passing data from one to the other and running all of them at the same time. When we put it all together, we coordinate by creating all the channels that are going to be the pipes of my application, the things that are responsible for sending data between different parts of the program. We create the first wait group, and then we run each one of my workers in parallel. So for each worker, we add one to the main wait group and say, I'm gonna run the worker one, and I'll send to it the wait group. So you pick the semaphore and tell me when you're done, and take the channels that you're gonna need to work on. So one of them you can use as input, the other one you can use as output, and then for the next worker we are connecting them by the channels. So in the first worker I'm sending channel 2 as my output, and that output in the first worker is going to be the input of the second worker. So one other way of thinking about this structure is if this was a pipe in the terminal. So if we think about worker 1, worker 2, and worker 3 might have been independent programs that we were running on the command line, we could communicate between them by doing pipes in the command line. So the channels are doing the work of the pipe, and the workers are all running in parallel like they would do in your shell if you do that example. So this is another visualization when we think about several workers. So we might think about each one of these parts of the program as being one of those workers, one of those sets of workers, because as we have seen before, we are going to spawn several goroutines for each one of the workers. And again, the main program is going to start all of them, and they are going to just send data between each one of them in parallel and run all of the same time. So what we are doing is actually not exactly this image, but we are kind of sending data down from one worker to the other, and we are passing data and separating completely each part of the program. So in the real world, what does this mean? This is real data, this is real program that we built at Mendelics where I work, and this presentation was all thought from this program and backwards. So this is a real program that we built to read a set of genomic data, of DNA data. So Mendelics is a genetics lab, and sometimes we need to read data from other sources. So in the beginning of this year, a project called GNOMED, which is kind of in the middle of the code over there, released a lot of data. This project was a huge project made all over the world, where several people had their DNA sequenced, and the result of all that DNA sequence built a huge base of mutations, what we call variants. Like the program has the mention of that concept, but we can think about mutations as pretty much the same thing for this presentation. So we received all that data, and originally we thought, no, we're going to have terabytes of data because there are hundreds of thousands of people that had their DNA sequenced and had the data displayed publicly. But in the end, the result wasn't that big, so they released a couple gigabytes of gzipped text files in a format called VCF, which is a format that is known in the bioinformatics community. So we had already dealt with that format before. We had already dealt with that kind of a dump of information. So we wanted to fully process all that data and extract from it information about population frequency of mutations, and then store it on a table. In this case, a DynamoDB table, but it could be any kind of outside part of a program, which we were going to use all that population frequency in other software that we do. So what this database had that was good for us was millions of mutations, like 300 millions of mutations in healthy people all over the globe, and that contained population frequency by ethnicity. So we knew if a mutation was common in an African population, but it was not common in a South Asian population, and that kind of thing. So it is helpful for us because we are trying to find mutations that cause diseases, and if a mutation is very frequent, it is not likely that it causes diseases because lots of the population will be affected by that problem. So a mutation that is not seen in this database, but we find it on one of our patients, kind of calls attention to it. So that is why we built this program. So it has the same pattern that we used before. So we are building several channels in the beginning, each one for receiving variants, for receiving things that fail to parse in the beginning of the program. The key channel receives the structs that have the population frequency, and then the accumulator is just to count with how many variants we process until that point in the program. And we start a Waitgroup at 5 because we are going to start 5 goroutines. In the real program, we are doing add 1 with each one of the goroutines, but it's pretty much the same thing. And then we start doing the real program. So we call the parse VCF function, which receives a reader. In our case, this reader represents the gzipped files which we are reading in the VCF format. And it does all the work that is specific about this file format inside of this function. And the problems that it has, it sends on the invalid channels, and the real variants that it finds, it sends on the variance channel. So the consume invalids function only receives one channel. Its only responsibility is to log errors and show us if something is going wrong. And then the rest of the channel, the rest of the program does the heavy lifting. So we are parsing the fields that we actually want from these variants, the population frequency fields. We are sending them into the other channel, the key channel. And as a last parameter, we are passing a parallelism degree, which we are receiving from a configuration struct with all of the options of the program. And we do the rest. We receive data from the parse nomad fields, and then we send them to this hash table. And if you think about this, it's pretty much the same pattern that we showed before, but you have access to everything you can do in the language. So these functions have more parameters than the example, or have less parameters in the case of the consume invalids function. These are not related to concurrency itself, but they are related to the thing that you are actually trying to do in your program. So we are reading our files, handling errors, parsing the information that we actually want, storing them on a database, and counting whatever we are trying to do. And all of this is run in parallel, so we will use everything that the machine we are running this program has available with pretty much only this code. So how did this perform? It was an extremely low memory consumption because the program pretty much only keeps in memory whatever it is working on at that specific time. Go is a garbage collected language, so whenever we are finished with a struct or an int or anything that is on the memory of the program, it is swept away and it is removed from memory at some point. So, and this happens very fast and very frequently. So this program pretty much only had in memory what it was actually working on. So it ran for 36 hours on an 8-core machine in AWS, and the program pretty much never went beyond 500 megabytes of memory. But in total, it was dealing with hundreds of gigabytes of data, and it was only spending the memory it needed for only what it could handle at that time. But we had a lot of control of the degree of parallelism of the program, so the slowest part of the program, where we are trying to read data from the variants, and where we are trying to send data to our outside program in the network, we could control from the outside of the program via configuration what was the degree of parallelism. So it was very easy to hit 100% of the CPU and to start hitting bottlenecks on the outside of the program, on the network, on the storage that we were using. And in this Nomad program, a couple million mutations could have been processed the time it took to reach this point of the presentation. So in the first time I did this presentation, I had only 7 minutes to reach this point. And back then I used to say, no, by now I did exactly 1 million, which was a kind of a better number. But now, since I had a little bit more time, we could have done something between 2 and 3 million mutations. And the whole system has a little bit less than 300 million, something like 270, 280 million mutations. So the largest database of human mutations ever known could be fully processed by this program in about 36 hours. So we ran it like once, and then we had to run it once more because you had to change something. And all of that took 36 hours in each one of the runs. So we simply started a single machine, a single normal machine. Probably if you are handling large amounts of data in your HTTP apps, in your web apps, you are probably using machines that might be bigger than this. So you have easy access to these kinds of machines in pretty much any cloud. And if we wanted, we could have used bigger machines, and the program would have scaled easily just by changing a few configuration parameters without recompiling, without anything. We would just run our container with the program, and it would spend more. You would use more CPU and probably not use more memory and run as fast as we wanted. So beyond the basics, what else can we do besides the things that we showed so far? There is a lot of things that can be done outside of this pattern. So there is a lot more that can be done. I pretty much used a pipeline of functions. They are being called just like a pipeline in the command line. But there's more than we can do. We can do fan in, we can do fan out. All kinds of topologies that you can think about a concurrent program can be applied using the standard library. So far, we have only used pieces that are directly related to the language or that are available in the standard library. And the only thing that we did from the standard library was one single struct. So we have all of the language available to us. We can use anything that is available. We can use libraries from the outside of the program. We are not bound into a specific kind of program. We don't need to run concurrency only in this way that I showed you. So a few things that we can do is buffers, selects, timeouts. So what are those? When I declare the channels so far, I have never said that I wanted more things inside one channel. So I never defined the size for my queues. So I said in the beginning of the presentation that channels are just blocking queues. So you might be thinking, okay, these are queues that only have one thing inside them. It's kind of weird. But yeah, you could have a queue that only accepts one thing at a time. But you can also declare when you make a new channel that you want to have a buffer inside it. So you want to have a bigger queue inside the channel. So this means that the blocking operations that doesn't need to be exactly one goroutine waiting for a read or send operation on the other side immediately. If you do an operation, if you do a send into a channel that is no goroutine available to read from it, and you have a buffer in the channel, you can still perform that operation successfully and store that data inside the channel. So whenever a goroutine tries to read, it will receive the data immediately because it is stored in the buffer. So these buffers store values in memory and make them available immediately. But in my personal use, they haven't been a very good idea. The first concurrent programs I did with Go several years ago, we built buffers into all channels that we used, and what happens when we had channels with real structs, like the ones we've seen on the real program I showed you, and this was only spending memory for no reason. So nowadays, what we do is we control the degree of parallelism of the program, and we make it use as much CPU as the machine makes available. So the program is always running at 100% CPU and always processing as much data as it can. So we are not buffering anything inside the program. We are saying, okay, the fastest parts of the program are being slowed down by the rest of the program, but that is no problem, because if we use buffers as a substitute for this, we would be spending memory to keep data inside the program to handle this difference in speed between the different blocks of the program. But at some point, we will probably reach the maximum capacity of the channel anyway, because the fastest parts of the program will send more data than the rest of the program was able to read. So you would hit, in this example, full channel with 2048 integers inside of it, and then the program would behave as if it had a channel without any buffers. So it's easier if you just do your program without buffers, and it leads to better memory consumption, leads to easier to handle programs. There is also a keyword that I haven't showed you, a control flow operation that I haven't showed you so far, which is the select. A select is has the same syntax as a switch case. You might think of a switch case of any language that has that kind of operation. And the select has exactly the same syntax as the switch in the Go language. So what are those for? Like I said several times in the presentation, operations on channels are blocking. So if you try to read or send something on a channel that is not ready to do that operation, your whole Go routine is going to block. It's not going to do anything else until it can stop, until it can be released from that part of the program. So what if I have two channels and I don't know which one I'm going to receive data from first? So I have different parts of my program sending data into the channel 1, different parts of the program sending data into the channel 2, and we want to read from whichever program gives us data first. It is impossible if we don't have a select. We're just trying to read from the first channel, and we're going to be unable to move on with the program because we are thinking, okay, we have nothing else to do until we receive data on the first channel. So if the second channel has some data to send, we are not going to be able to read it until we receive data on the first. So if we want to use both of them together, we need a select. So if we do a select case, it's gonna the select structure is gonna release us with whichever case has data first. So either the first channel or the second channel, it doesn't matter, the order. And if we do this in a loop and we receive data from these channels concurrently, we may receive data in different order. So what if I can't block as well? I showed the example of, okay, I'm going to read for two channels, but what if I want to control a single operation? Select can do that too because they have the default clause. Just like a default clause in a switch, if we do a switch and we don't get into any of the cases, we can do a default, which is there is nothing there to do. So we can use this to do non-blocking operations on channels. So if we do a select, trying to read from a channel, and there isn't something there, we just go into the default and we do whatever we need to do in the rest of the program. And the same thing for the send. All of the channel operations can be used with select and default. And if we have data ready for the program at that point, we are going to enter the case. And if we don't, we're going to enter the default. And what if I can only block for a while? I can't wait for a channel to give me operations, give me data, but I can only wait for a specific amount of time. So I can use the time package and the after function. So if I just use time after a specific amount of time, the after function is going to give me a channel which is going to send some sentinel data inside that channel after the time I specified. So in this example, I'm going to try to read from the CH channel, and I'm going to wait for 2 seconds. If 2 seconds pass and I didn't receive anything on the first case, I'm going to enter the second case and I'm going to abort. So I can use the after function to control how much time I'm going to wait for each one of my operations. So there's a lot more that you can do with this. You can use the context package as well for cancellation. So you might say, I'm running my program in parallel, I'm doing everything I want concurrently, and I receive a Control-C, or maybe I'm using an HTTP2 server, and I can recognize when a request was canceled. So you can use the context package to tell the rest of your program, don't start any big computations, just end what you're doing and finish your program cleanly. So the good thing about all of this is that you have the whole language available. You're not tied into one single type of program. You're not tied into a single topology. You're not tied into doing just fan in, just fan out, or just the kind of workers that I showed. So you can do everything that that language gives you, and everything is simple. Most of the time, you don't even need to use these select cases. Sometimes you're going to have a few programs that you want to do these operations with a little bit more control. But most of the time, you're just going to read until your channels are fully processed. And you're going to just do a simple pattern with workers. And you can control your program really well with only that. So that's it. Thank you.